To explain what it means to change the KSK of the root zone, I have to explain the roles of keys. Keys have different jobs. Just like house keys and car keys have different jobs, what they do, what they unlock, what they start. We have a bunch of keys that act differently inside the DNS. And I'll mention three things here. They're not really keys, but they're parts of keys that will help me explain how this is all put together. We have a KSK. It's called a key signing key. It produces signatures over keys. ZSK will come up. That's a zone signing key. That's used to sign everything else in the zone. And the DS record actually is a pointer to a key which lets me link all of these keys together in the DNS. Now, I have to explain this because we invented these roles of the keys a long time ago because it was going to help operators run this system a little bit more easily. The big result is that it made explaining this thing very hard. Okay, so back to what we're trying to do here. In this checking, you get data, which is up on top in the blue box up there. It's blue on the screen. You get back the digital signature, and you have to get a key called a ZSK, and you put that together through a cryptographic function and either get yes or no. Is this going to work or not? This means something if you trust the key at the bottom. And the way that we trust the key at the bottom is because it's at the end of a chain of trust, a chain of keys that sign each other. The ZSK, the root ZSK gives you the root KSK gives you the root ZSK, which gives the DS record for the TLDs, and so on down in this chart here. Now, the reason for this chain is because it's not just a one-shot. This is not the only thing in the internet. There are a lot of other, there's a lot of fan-out. There's a lot of wide dispersion in the tree of this. The root KSK signs the root ZSK, but that ZSK then signs about 1,300 different DS records for all the TLDs out there. So now we're going from 1 to 1,300. .com has about 500,000 DS records inside of it. So now you go down to 500,000 different chains that we're looking at for this. I don't know off the top of my head how many others are signing other TLDs, but it gets pretty wide pretty fast. So what I'm going to talk about the topic of this talk is that root KSK up on top. It's going to be the start of all of these validations out there. And that's what we're operating at ICANN. And that's what the change is going to be concerning. So how this translates into what it means to you is that we talk about this thing called a trust anchor. When you do the DNSSEC validations and you want to go down that chain to the key you need to validate the data that you're trying to validate, you start it with this one key. It's called a trust anchor. And that trust anchor is the one thing you have to have full faith in. If you're the operator of this recursive server, if you're checking anything, you have to decide that this key is something that I will always trust it and let everything else build up to it. Now there are a couple of ways to do this trust. You could do it implicitly. If you are someone who downloads software and just likes to run it, that software likely in the DNS world will have the KSK burned into the software. And if you just run it automatically, like some of the tools let you do, you're implicitly placing trust on that key. Other hand, you may decide that you really want to make sure this is the right key out there. You may take the key and compare it to different sources. That's an explicit way of doing key. It could be a very manual process. It could be very automatic, depending on how you work it. That's all up to the operator of the zone to decide how, operator of the network or the ISP servers decides how they want to do that. So one of the assumptions people make is that the root zone KSK is the trust anchor. It's really, whether or not the root zone KSK really is the trust anchor you have to use, it's up to you. You decide what you want to do. Now, by convention, we use a root zone out there. By convention, we can trust the keys out there. Even whether or not you want to use different keys, it might be that down in the tree that there's a break in the chain of security and you have to add some other keys out there. There's other things other trust anchors potentially for someone running a recursive server. But for this talk and for most of the assumptions about the general operation of the internet, the root zone KSK is the trust anchor that would work best for your servers on the internet. So I also want to talk a little bit about how the DNSSEC is put together at the root zone to help put this, put together why this project it matters to folks. Right now, the DNSSEC in the root zone is actually managed by two different organizations, ICANN and VeriSign. Each run separate parts of the DNSSEC process here. ICANN, we run the KSK, we operate the KSK. We have the lifecycle management under our jobs, and we sign the ZSK for VeriSign. VeriSign's job is to produce the actual root zone that goes to the root zone operators. In doing so, they run the ZSK, they sign everything that's in the root zone, and they send it out to everybody out there. We work with VeriSign on this. We have different jobs. Our duties are separate, which is actually good that we check each other's work. But we do coordinate, and when you may hear VeriSign talk about the ZSK operation separate from our talks, be assured that we have coordinated at some point beforehand to know what each other is doing. In fact, we can't do much with the KSK without VeriSign also making the same kind of work with the ZSK. So the root zone KSK, it's been the one that's working today has been there since 2010. It's in hardware security modules. We keep it in a couple of facilities out there. There's a whole set of talks we could give you on how that's put together, but there's not time for that today. This key has been in place since 2010. It's never been changed. You can get the key today a couple of different ways. The key is in the DNS. You can ask the root zone, the DNS, do a query for the root zone DNS key set, and you can pull it out. If you are using that to start doing validation, be careful that you get the right key, because if you're under attack at that moment, you may be misled. But when you're trying to protect the DNS, and you don't really want to rely only on the DNS for the information. It's a security issue. We also have a website, a file on the web that has the keys in an XML format. There's information there for knowing how to pull that down and make use of that. Also, you can check the two. Although both of them still are on the internet, you can still be attacked. And there are other ways. The code that's being distributed out there, we've talked with the distributors of the DNS software that you can get, either buy or download. We make sure that they have the right key in there. But there's also the other ways. So check it with other means, just to make sure. Like, you look at, we used to have T-shirts with the key on it. You can go any place else that's harder to forge and just make sure. One operator told me that he wants many different ways of getting it. He just compares them all. If they all compare together, he's fine, and he goes forward. So we are going to change the root KSK, and this is a first-time thing. We've never changed the operational KSK. We actually have made a change, but it didn't matter because no one knew about it back then. But this is the first time we're changing where people have been doing production work on this. It's precedent-setting in a couple of ways. This is a project where we have to do something, and anyone else out there using this key has to follow along. The problem is nobody knows who all the other people are out there. DNSSEC is opt-in. You decide whether you want to run it or not. You don't tell anyone you're running it. It's even Now, one of the questions we have about this project is, why are we changing this? First of all, one observation I don't think I have on here is that there is no evidence that we need to change the key. The key is not in danger. The key is not broken. It's not getting old. It's not scaling. It's scaling perfectly well. It's performing well. But we know that for security purposes, anything that's a secret doesn't remain a secret forever. We can't count on this always being a secret. At some point, something may happen where we may lose the key. We may have someone be able to steal the key. So we have to at least account for changing it at some point. Now, the next part of this is, as an operator, you know that if you ever have to do something in an emergency, you want to make sure you practice it first. For pure operational sanity, you do something in normal conditions before you have to panic and do it. So we're doing it in a case where there's no reason to do it. We're going to do it now when everything else is normal. And why aren't we just doing a private test internally in-house to make sure we can do this? The problem is that this involves people out there we don't even know who they are. So the only way to do this and test it is to actually go through the process of doing the whole thing, a live test with the developers out there, making sure they're ready for the software. Operators out there have to be able to see this and follow all of what's going on there. And we have to rely on communicating with as many people as we can in the operational community to say it's happening. The bottom line is that changing the root KSK will impact anyone doing validation of DNSSEC data that involves the root zone. Anything below the root zone without any other trust anchors in there. There's a, and if you're doing this, if you have trust anchors put in there, you want to make sure you maintain them. There's a whole topic of trust anchor management that I really would like to get into someday. Maybe we'll have that talk in the future, but we have to learn what it means to manage your trust anchors that are out there. This is actually the part of DNSSEC which you can't fire and forget. Everything else can be pretty much automatic now. So what is the meaning? How big is this project? Right now, according to Jeff Houston, and when I say his name, you know this is good statistics because he does really good work out there. I've warned him, I'm mentioning him in this talk. 15% of resolvers out there show evidence of DNSSEC, if I have that correct. So about 15% of the resolvers are going to need to have some maintenance of the trust anchor at this. DNSSEC signing, we talk a lot about that. That is not affected by this at all. If you're signing zones, changing the KSK up there is not something you have to worry about. If you're validating, now is the time to start looking at how you manage your validating DNSSEC servers out there. The root zone, the root KSK hasn't been changed before, so perhaps those who've rolled out DNSSEC and set it up there may be doing something implicitly they don't know about. They want to make sure that they can change this key or make sure the key is used correctly or is being followed correctly by themselves, their processes, or the software. So I started out saying that we have a plan. We have a project that's going to go out there. We have plans for the project. These documents are available from that website up there. These are the projects. These documents describe what we anticipate doing through this. We have a bunch of different plans in there, and we encourage you, if you're interested in this, to take a look at these. We don't have a formal feedback mechanism. We have had feedback to the process earlier, but read them for your information. If you see something that is really wrong, please let us know. We're not going to ignore comments. We don't expect to go through a comment process for this, a formal comment process. So in terms of overview, October 11th, 2017, which is a little more than a year from now, we will change the key if everything goes as planned. So we have about a year to make sure that you have things done. You have some time to look at this. On October 11th, the KSK that we're using today will no longer sign. And if that's your trust anchor a year from now, or a year and a few days from now, you're going to start invalidating everything that comes in. You're going to see the entire internet go off. Even for data and zones that are not signed, your servers will knock everything out by saying there's nothing valid anywhere. I can't go down to where it says there's no security below that. Now the plans we have, we're retaining the current cryptographic settings, and that's the real meaning there is we're still using the same algorithm we're using today and the same key length we're using today, which is RSA SHA-256, 2,000 bits, roughly. We considered other algorithms. We may reconsider not going to that for the next time around. But right now, we're keeping the cryptography to look the same as it is right now. We're following this standard called automated updates of DNSSEC trust anchors. Many people call that RSC 5011. We will follow that. You can follow it if you feel that's the right way to go for you. It's an automatic way to update this, but we understand not everyone will use that in production. The roll actually is taking a long time. We were going to create the new key on October 27th this month. So it'll be almost a year if we create the key before we press into service because we're not in a rush. There's no reason we have to rush this. We're going to take our time, do it within the schedule of events we have right now. So we're not going to be trying to make us go faster. We could, but we don't want to. We also are going to set up and do some testing and monitoring of this process. We're going to watch how it rolls, see what happens. We're going to provide places for operators to come in and run certain tests, and I'll get to that in a future slide. So in the process of setting up this key roll, one of the things that we've been concerned about is the response size. You know, DNS is very size sensitive. It just started out as a very small response. It's grown over time. DNSSEC has gotten bigger. We hear about DDoS using it as a payload amplifier and so on. In this process, we will grow one of the important responses to over 1,400 bytes. 1425 bytes initially, and then later on it will go to up to 1425. That is the highest of the whole project. We've been looking at this in terms of IPv6, and V6 fragmentation doesn't sound very compatible with this, what's happening. On the other hand, we've never seen any evidence that this has caused an outage. We know that there are TLDs out there with very large key sets, so we're kind of watching this right now. We believe it will work. But it'll work in certain conditions. Number one thing is make sure TCP is running. DNS TCP is a fallback. You may have to use that to get to the root zone for the keys for this. We want to make sure that people don't look at the size of the messages, the key filtering. That's historically been a problem. Some tools filtered out everything at over 512 bytes. Those days hopefully are behind us. But we want to make sure that DNS works healthy through the network. In fact, in general, you want to make sure your DNS servers can take larger and larger responses because of this. IPv6 fragmentation DNS. I have another slide on this because I have to mention Jeff Houston again. That's two, Jeff. Jeff did a lot of work for us. He looked at this thing. The problem in IPv6 fragmentation is that it doesn't fragment in the network. So you have to send it out fragmented ahead of time, or in pieces ahead of time. In the idea of IPv6, from what I understand, and I'm not a v6 expert, despite listening to it for many years at conferences, if you send out a very big message into v6 and it needs to fragment, it doesn't help you. It sends back a message saying, I couldn't fragment this, I just dropped it. The problem in DNS is DNS is like, it's got amnesia. It forgets quickly. So when it sent out this piece of message out there and it gets back, it was too big, the DNS didn't know what it sent. So DNS is it's got a problem with this. It doesn't really go very good with the DNS plans out there. That's where TCP is going to probably be needed to get around this. So Jeff actually has a really good post on this. I wished I could present that to you, but it's too much to put into a few slides. So I have a URL there. I recommend looking at that to get incredible detail about what the issue is. In the recommendations, at the bottom, there's the TCP over v6 should use an MTU of 1280 bytes, and there's justification in there. And UDP, it's interesting what should be done there. And I have this but in quotes, because that's paragraphs of but in there to explain it. So really consult this article, listen to Jeff talk about this. He can say much better than I can. We have to watch this. This is our concern here with the fragmentation issues. As far as the project, again, the dates to watch out there. September 19th of 2017, next year, we will grow sizes to 1414 bytes for 20 days. Fragmentation might be an issue then. That's the first time we're concerned about this happening out there. October 11th, I mentioned already, that's the date where we change keys, and if you haven't followed along, you're going to be stuck at this point. And January 11th in 2018, which is 2 calendar years from now, so we're talking a long span time, we will hit that 1425 byte high for this, and again, we're going to watch for the fragmentation. By that time, we'll have a better idea of how this actually will play out. Trust anchor management, this is again, now the focus on areas that operators should look at is look at how you trust and configure data, and not necessarily just trust anchors in DNS, but in cryptographic terms. All the certificates you use, we all know what happens when a certificate expires in operations. It's a real pain. Cryptography is that way. You have to check the timing. Timing is very important for all this. You have to decide here, are you doing configuration control systems? Are you doing centralized management? Are you doing distributed management for your software? Is embedded data something that you rely upon in there? And one thing, if you're running DNSSEC, look for the failures you get and see how people are recovering from that. Because people, in evidence that we've seen, is some people will start DNSSEC and DNSSEC will fail, but they'll fail over to non-DNSSEC. And so the user may not really notice that DNSSEC failed. But as you're an operator, you should make sure things are running efficiently on your network. Get familiar with the automated updates of the DNSSEC trust anchors. And again, RFC 5011, I don't have it on the slide. See if that's something you want to run. If you have the software software that you're probably running for DNS right now is probably capable of doing it, and decide whether you really have it set up to go, whether you trust it, and so on. But also, one other factor here is negative trust anchors. Sometimes people make mistakes and you don't want to pay for it. There's a famous example of one site that didn't perform their key role correctly, and an ISP got inundated with trouble reports saying the internet's down. And so they had to turn off DNSSEC for that particular case. Tools and test beds, but ICANN are working with developers to make sure that the software that you download and use, or purchase and use to, is up to the job of rolling this key. This is a new thing for everybody out there. I've been asked to talk to them about tools for debugging and make sure it's easier to manage this. Updating the keys that are bundled, we're talking about doing that too. Currently, there are some test beds out there, but the current test beds are really more useful to those writing software. And I have the two URLs listed up there right now. If you're writing software, it's a good thing to test against. Probably this crowd is not going to use that as much. We are internally developing test beds that would be more useful for operators. What that means is that the test beds will be running in the real-time parameters, so there'll be no changing of magical parameters in the software to see whether or not your code and your configurations actually are doing RFC 5011 automated updates practices. And these are targeted for the end of this calendar year before they'll be released. And that to give you at least still 6 months before you even start seeing anything happen, or 6 to 9 months before you have to do this. For more information, we have a mailing list up on top. The first link is for the mailman page to subscribe yourself. Twitter, and there's also a web page off of the ICANN.org website, which has a lot of detail about where we are, what we're doing, and how the project is going. So with that, I'll open it for the chair to decide what I'd say next.
Any question to Ed? Jeff has a question.
Yes, please state your name.
If you're ever going to contemplate an all V6 network, because V6 and the DNS is currently a really bad fit. And what's saving us is dual stack, because the V6 for large responses fails, and hopefully your resolvers also have a V4 address, and V4 does much better in fragmentation and big packets. It's just, that's the way it is. But the key message here for all of you who are running DNS resolvers for your users is you have to go and look at your configuration. And if your contractor, your friendly DNS person, left the clause managed keys in your DNS, you're toast. You have to run auto-managed keys for this key role to work. Otherwise, you've got to be on the ball for every single critical date, and you won't be. Because if you've got managed keys, you're probably in a dire situation anyway. So if you're responsible for the DNS, go check and make sure you're running auto key management rather than manually configured management, and the rest of this stuff should just work for you. And I think that's kind of the bottom line that I took away from all this.
Yeah, thanks.
Anyone else? Thank you, Ed. Thank you for your time. So our next presenter is from India. His name is Anurag Bhatia. So before the presentation, I want to ask a small question to our Sri Lankan brothers and sisters. How many root servers are present in Sri Lanka? Anyone can volunteer? Yeah, really, I didn't know how many root servers are in Bangladesh. So let's know from Anurag Bhatia. Anurag. No, not you.
Wait, second slide. Which one? Yeah, this? Okay, this works. Thanks.
So good evening, everyone. I'm Anurag from Hurricane Electric. We're an IP transit backbone, and we sell IP transit, data center services, etc. Today I'll be talking about root DNS servers, how well Anycast is working for root DNS servers. These statistics are based primarily for Southeast Asia, so I'll be talking about region from Afghanistan, Pakistan, India, all the way down to Maldives. And a considerable amount of this data is based on RIPE-at-less probes, so I'd be spending some time in telling you about that. Before we proceed, what are the root DNS servers? These are the authoritative DNS servers for the top-level domain. So for instance, .com, .in, .lk, .bd, all these are there and on the root zone. And these root servers act as the authoritative servers for these zones. These are the ones which know that they have the glue records to each of these TLD servers, and they help in the resolution. Logically, there are 13 root DNS servers. These are named from A root all the way till M root. And this is a logical number. It's very important to note that in real, there are way more root DNS servers, and these are heavily anycasted. So 13 is the unicast addresses. 13 is the unique addresses which are anycasted across from different locations. This map shows some of the numbers over here. Quick introduction on Anycast. Anycast is all about announcing the same address pool from multiple locations. So if you go by the way BGP routing works, if you have different prefixes in your routing table, and for different routes in your routing table with different next hops, BGP is expected by default to take the nearest exit as per the hot potato routing. So in theory, networks are expected to hand off traffic as quickly as they can, and Anycast just works. So you can have different servers using the same IP across the world, and everyone will just hit the local server. But that's in theory, and it breaks a bit. That is this study about. In general, it works very well when you have lots and lots of peering and limited set of transit. But if you have a mixed set of transits at different locations, Anycast pretty terribly fails. And that's the next point about that networks have their own flavor of local preference towards other network. So if you happen to have transit from one provider in one location and another provider in other location, there is a high possibility that, that you will have a sub-optimized routing, because everyone prefers their customer routes over the routes they learn over peering, over the routes they learn from transit. So testing methodology. As I said, the study is based on the data we collected from RIPE Atlas probes across this region. RIPE Atlas probes seem to be one of the best possible tool we have right now, which is quite spread across. So it's a small device, around 9,000 of them, and they are spread across the world right now. And in this region, there were relatively lower number of RIPE Atlas probes, but still it was better than having nothing. So we triggered the queries for id.server on each of the 13 root server in the chaos class, and we figured out it works for 9 out of 13 root servers. And it happens to be that remaining 4 root DNS servers, they do not support id.server, which happens to be a newer query, and they support the older one, hostname.bind. My good friend Kabindra from PCH told about that, and we eventually redid this study by using hostname.bind. For observing latency, we use the simple ping from the Atlas probes, and this works for 12 out of 13 root servers. It's just that groot somehow is filtering the ICMP. So from all further data I present, groot is excluded from the latency comparison. So here's a quick table showing that in case of id.server, broot, croot, groot, and mroot, they did not work. For hostname.bind, it pretty much worked with everyone. The interesting thing is that even though we are hitting extremely likely the same server, hostname.bind gives a slightly different reply than id.server based on the mappings root DNS operators have done. And this is also one of the limitations, that there is no standard mappings. Some of them use name of city, some of them just use name of the airport code nearby. So it's slightly inconsistent. It's hard to automate this kind of observation. Basic idea of RIPE Atlas probe. I thought to take this opportunity to tell you about RIPE probe. So this is a small device, as you can see. Oops. So this is a small device. It comes with an adapter, and charging cable, and an Ethernet cable, and it does some basic measurements all the time. So whenever a RIPE Atlas probe is connected in a network, it keeps on measuring latency and the trace routes to root server and certain other predefined measurement. In case you are not hosting a RIPE Atlas probe in your network, you should host one, and I have got a few of them with me, so you can just contact me after this, and I'd be more than happy to distribute you those. And it will help in triggering out these queries out from your network as well at a later stage. This is the coverage map of RIPE Atlas probe, and since it is a project from RIPE, we can see it's quite heavily deployed across European region and decently across the American region, but South Asian region, it still misses quite a bit. And this was also one of the challenges in our study, that there are relatively very few probes in, say, case like Afghanistan, where there was almost 0 probe, and we could not trigger any traces. Some of the limitations of this data: there's no way to practically test IPv6, because in the developing world, although in the world as a whole, IPv6 is still not very well deployed across the last mile networks, where we see ripetless probes. But in the developing world, the deployment of V6 is still very low. So practically, it's almost impossible to have IPv6 testing of this data. For instance, take example of India, where we have around 50 ripetless probes right now, and I believe only 3 of them are on IPv6. Hostname and ID, hostname.bind and ID.server replies are not standard, and this makes it tricky to automate this part because one needs to actually look at the strings and analyze where they actually belong to. Some of the root server operators are using standard airport codes in the reply, while some of them just use the city name, so it's tricky to pass that data. There are low number of probes, as I said, that's one of the challenges, and one important fact here is the diversification of ripetless probes. We see this case in quite a few countries where a lot of probes are placed in the same network, and they can be even in the same city. So if that network happens to have bad routing, we are going to have bad data, which might not represent the actual country data. So it is extremely important to have more and more probes across different ASNs, across different geographies, to have this kind of measurement to be done. And a considerable amount of ripetless probes run on the last mile network, which happen to be DSL, and they add up their own latency in the start. So we have overhead latency right on the second hop after the router in the data. So these are the countries this data is about: Afghanistan, India, Pakistan, Nepal, Bangladesh, Bhutan, Sri Lanka, and Maldives. If we talk of root DNS servers, there seems no root DNS server in Afghanistan. And in case of India, we have got around 9 root servers, 4 in Pakistan, 3 in Nepal, 4 in Bangladesh, and so on. And in Sri Lanka as well, there seems like presently there is no root DNS server. I heard there was one, but maybe it's under maintenance. So I even tested out just a few minutes back, and I cannot see getting routed to any of these root servers. So, in terms of ripetless probe, when this study was done, 0 probes were active in Afghanistan. And in terms of India, we got 50 probes, 7 in Pakistan, 15 in Nepal, and so on. So except for Afghanistan, in other places, we had enough probes to trigger out the traces and ICMP and DNS queries to find more. Coming to our data for India, we have got JRoot server in Delhi, KRoot in Noida, and in Mumbai we have got 4 roots, D, J, I, and L. So a reasonable amount of distribution. KRoot, I believe in Noida is turned off from a while. When we did the study at that time, it was under some issue, so that it did came up in the data. While iRoot and FRoot happen to be hosted at Mumbai and Chennai in Nixie. Here's the data for India. So in this table, I'd be using this table as a standard table across for the whole data. You can see ARoot is not locally present, and we have an average latency of 264 milliseconds. And we distributed the query output into 3 zones: queries coming from within the country, which are being served from the region. So for instance, in case of India, we assume the region in Asia. So if queries are being served out of Singapore, we call it within the region. And out of region is usually when queries hit back to root servers in Europe or US. So root servers which are not locally present, we expect 0% to be within the country. Here we can see iRoot performed relatively well with average latency of just 47.97 milliseconds as tested from around 50 ripetless probes. And there was another server, eRoot, which was still giving a reasonable latency because a lot of the traffic was staying within the region. And for remaining, a lot of traffic did went out. And KRoot here, we can clearly see it is present within the region, but 0% of the queries hit KRoot because it was under maintenance. And here's latency distribution for India. So we can see I is in much better state, while A, B root server, and H root were showing much higher latency. On the right side, you can see local server latency versus non-local server latency. So we had an average of the latencies which we saw with the local versus non-local. And here we can see around 100 milliseconds for the servers which are present locally. And this data is quite degraded because of the K-root factor at that time. Coming to Pakistan, There are around 4 root servers in Pakistan, L root in Islamabad and Lahore, F root and I root in Karachi. And there were around 7 to 8 ripetless probes, if I remember correctly, from which we triggered the traces and data. And in this case, we can clearly see out of those 4, 3 did show, so there were 4 servers with the overlap of the L root. So out of 3 root servers which are present in Pakistan, latency is much better, F root in F, I, and L root. But still, a considerable amount of data still hits outside. So even when F root happens to present locally in Karachi, still around 50% of data was going out of region. And not just out of country, it was going completely outwards towards US or Europe. And this shows Anycast does fails at times. And similarly for I root, only 33% of the probes were hitting the I root. Rest were just going outwards. And this has been, the data was verified based on the chaos data as well as the trace routes. So in the cases where we saw data to be reasonably out of way, we went for the trace routes, and trace routes do show it hits outside. L root showed very good performance, 24 millisecond latency out of all probes. All the probes hit L root. And it would be very interesting to see what is the difference in peerings of L root as compared to other F and I roots if we have someone local present over here. So latency distribution, as we can see, L root gave much better latency. In rest all cases, the latency was much, much higher, usually close to 200 milliseconds. And in this case, local server versus non-local server, we had a difference of 80 milliseconds for the local versus 220 milliseconds for the servers which were not local. Coming to Nepal, there are 3 root servers, D, E, and I root server in Kathmandu. I believe they are hosted at NPIX, if I'm not wrong. And all of them show pretty good latency. You can see average latency of less than 100 milliseconds in all the cases, and even for E root, it's just 23 milliseconds. And the source points are same over here. So it's the same probes which are querying for D root, and it's the same probes which are querying for E root. But it shows something is good, specifically in case of E root over here, which is giving much better latency as compared to D and I root. And in terms of failure of Anycast, here also we can see a considerable amount of data going outside in the region. And the good thing is it's still going outside of country within the region, but not going completely outside because of a relatively good peerings and good connectivity from the other players within the Asian region. This was slightly different in case of, say, Pakistan, and I would assume it would be very different if we had probes in Afghanistan as well, because a lot of providers in Pakistan and Afghanistan tend to go for connectivity from the international providers rather than on the Asian side, and that's also based on geographic factors. In case of local versus non-local, the difference was 70 milliseconds versus 238. Coming to Bangladesh, there are 4 root servers in Bangladesh, all of them in Dhaka, D, E, F, and J. And in terms of latency, all of them showed pretty good latencies, usually less than 100 milliseconds, except for F root, which is just a little above 100. Still a bit of traffic went outside here as well, almost half of the traffic for D and E. And that shows that probes in those larger providers are still not paired with these servers. Maybe it could be that they could be down at that time, and we did not run this test multiple times. It is just done at one time. It's a one-sided picture. For the local versus non-local, 78 versus 211 milliseconds. Coming to Bhutan, there's one iRoot server over there, and surprisingly, that root server does shows better latency, but other root servers also have a good latency for D and E root, just 100 milliseconds. And it seems like some of them are hitting nearby in Singapore or India. Quite a few providers over there are connected with either either to the providers on Indian side for transit or to the providers in the Singapore side. Local versus non-local, a huge difference since only one server was present. And I'll come to the factor on how much difference a server makes if there's only one server present or there are all 13 roots present at the later part of the slides. Data in Sri Lanka. So in Sri Lanka, there was no root server present at the time of study as well as till now. And the only root server which showed less than 100 millisecond latency was the JRoot server. And it seems like Sri Lanka is hitting JRoot in India, somewhere in Mumbai, and latency was less than 100 milliseconds. But for rest all, the latency was much on the higher side. And if you look for the traffic, percentage of traffic going outside the region, it's very high. So it shows that a lot more peering is needed, especially with the root servers, to have a much better routing. There's no comparison of local versus non-local, since there's no server over there. Maldives, there's one JRoot server in Maldives. And other than that JRoot, other servers do seem to have reasonable latency of less than 100 milliseconds. And that's again based on the connectivity of Maldives with the nearby regions. Although it's still good to have more root servers always. So country-wise latency distribution. Average latency with 9 root server in case of India is somewhere around 161 milliseconds, 186 for Pakistan, 196 for Nepal, 166 for Bangladesh, and so on. And this does shows that peering does matter, and having more root server does matter. I'll come to the conclusions on that part in a few seconds. So an important part here, why does Anycast fails? When we have a local root server, we do expect traffic to route to that root server, but that's clearly not happening. So one extremely important reason here is that larger ISPs always put higher local preference towards the routes which they are learning from their customers over peering over the routes which they learn from transits. So at times, a provider might be just preferring a route where it makes more economical sense rather than the sense in terms of latency or performance. And that is fine, they have to be in business, and I'm not against that idea. BGP best path is not always geographically best path. There can be instances where you have a root server locally and it is 2 or 3 AS path away, while you have a server far away with which you are directly peering, and that's just next to your AS. And there's a tendency that Anycast will break in those cases. A lot of times Anycast does breaks due to route leaks. In case of K-root, for a considerable time, specifically in the Asian region, in India as well as in Sri Lanka and Bangladesh, we saw a lot of traffic going to one of the K-root instances in Russia, even when the K-root was present locally in multiple parts. And that was because of the route leak happening over there. And it can break a lot of things because it is hard to validate announcement if they go beyond a point. Unless they are filtered properly near to the source, it is tricky to filter them at a later stage. And providers tend to have different local preferences. So if you are learning a route leak from one of your customer, there's a high tendency you are going to prefer that route, and it is going to break Anycast pretty badly. And the last important point, use of no export. So no export in case of peering routes for the root server is a debatable topic, whether we should use. It's good in certain ways, and it prevents major route leaks from propagating. No export will ensure that route stays within the next networks, peered networks ASN, and is not propagated beyond. But it's bad in ways that you might be blocking the genuine case of your provider's customer learning that route. And if the provider's customer happen to be a multi-homed customer, it's going to be a bad case in performance. A standard practice which root server operators used to use in past, and still a lot of them use, is to have no export with a /24 and then a /23 without no export as possible fallback. Miscellaneous points about the study, an extremely important one. End users always speak to the DNS recursor, and they don't speak to the root servers directly. So root servers, whatever they reply is cached, and it stays there for a while. So this latency does not necessarily equates to the latency which end user gets. There are a lot more things in there. And even the presence of a single root server that does impact. So if you don't need to have all 13 root servers in order to have better performance. Even if you have a couple of servers, recursor algorithm will start pushing traffic to those root servers as compared to the ones they are pushing far away based on the performance data. Bind and most of other popular recursive software do that. Okay. And users who do not use local ISP server and they rely on popular server, they have altogether very different paths. So this data is not applicable in cases where you are using 8888 or OpenDNS. It's far different. And if you happen to run or if you are going to design a CDN network, which is relying on Anycast, then it's better to buy IP transit from a network in a larger geography rather than from localized player. Because if you happen to have a mixed set of IP transit providers, it's going to break Anycast pretty badly. Conclusions, more root DNS servers are good for country. They reduce the latency considerably. And it's important to have IXPs where we can have root servers and where we can facilitate peering with the root servers. And apart from latency, having more root server does helps out in impact of any major cable cuts. References, RIPE@list project and root zone and root server information over there. Thank you.
Any question for Anurag? Just very quick. Huh?
Yes, Aftab Siddiqui, Intelligo Networks Australia. Just want to comment on the results of Pakistan. We have been seeing these results for quite some time. This is happening in Pakistan because one of the major root server, that is froot, which was deployed in one of the ISP, who decided to de-peer with one of the major transit providers in Pakistan. Okay. That's why there's a 50% reduction in traffic. And they have decided not to accept any routes and send everything back to Europe. So okay. If all their customers are going back to Europe and getting the froot responses, that's why there's a high latency and 50% decline in responses. Sure. And the issue is same for the iRoute. The other provider decided to ditch the other transit provider because there are only two in the country. So there's a good reason why you have to have an IX in the country, which should be enabled pretty soon.
Sure.
Thank you.
Makes sense.
Jeff?
Thanks.
With respect, I'd like to humbly disagree with your conclusions almost completely.
Okay.
The reason why we went to an Anycast system of the root servers was not to, quote, improve their performance. Not. The reason why was after a rather difficult DDoS attack on some of the original 13 boxes that almost took the entire DNS system down. And the Anycast architecture made it resilient to those forms of attack because you couldn't mount a single point attack against an Anycast cloud. You have to really up the attack space to do that. Mm-hmm. So it wasn't to improve performance. And secondly, it doesn't improve performance. Because if you look at the whole thing from an end user perspective, the questions they're asking where answers aren't given that are useful, i.e. real names in the DNS, come from cached names almost all the time. The profile of queries to the root servers is a large number of nines, 99.99%, NX domain crap. And quite frankly, whether you serve the answer now or next week for an NX domain makes no difference to the user. There was no good name. So there's this mythology around Anycast clouds that more is better. The only reason why more is better is to defend against attack. It has nothing to do with the end user experience. And the message to Sri Lanka or India or anyone else is actually, this won't make your internet go faster. It will have no impact whatsoever on that outcome. The only reason why we're going to all this pain and effort is to isolate the route from individual attack vectors. Sure. And that's the benefit. And that's a fine benefit, but that's all there is. So I kind of wonder what you're trying to conclude by measuring the performance of the route Anycast. because it doesn't actually illustrate anything that relates to a user experience. And that's the key issue here. If you're trying to benefit the end user, you want to think about the routes in a different way. And might I humbly suggest from a conversation that you and I had this morning, there's a draft around the aggressive use of NSEC3 that can actually turn every single recursive resolver into an authoritative root server and authoritatively answer signed root queries with NX domain appropriately and relieve the entire problem. We don't need to get into larger anycast clouds to achieve that outcome. We can do better differently. Thank you.
Sure. Quick replies on those points. So in terms of DDoS absorption, yes, extremely important point. I think I should have that in my slides. So yes, it makes sense to have more root servers to absorb DDoS locally rather than that having to all the way go forward from your limited submarine cable capacity to the other countries. In terms of how much impact it has or whether we need root or not or whether we should have local roots, that has more to do with deployment of large-scale DNSSEC. If we have more and more resolvers doing DNSSEC, we can actually have much more local DNS servers. We can even have a box doing all 13 routes and just have a legitimate reply from it and validate it based on the signature. Yeah, that's pretty much it.
This is Kazunori Fujiwara. I have a comment about the measurement method. Live-path probes may record DNS response time or should record. It may be the same as ICMP ping response time, and then you can plot G-root response latency.
Yeah. Okay. We can take this offline later on.
Yeah. So thank you, Anurag. Our next presenter is from Japan, Kazunori-san. And the thing is that he has a very good research on this IP container dispersion. I really don't know what is that. Please.
Can I see as a case? Hello, I'm Kazunori Fujiwara from JPRS, Japan Registry Services. JPRS is JPRS is JP country code top level domain operator. Today I will talk about page one. Okay, thank you. I will talk about analysis of RD0 and RD1 queries seen at root and JP. I would like to know DNS query trends. Are DNS queries increasing? How much queries does each IP address send to root, JP, root and TLD? Is IP version 6 deployed? Is DNSSEC deployed? And why some addresses send RD set queries to root? To analyze these data, I analyzed two datasets. One is DNSOAC's root dataset. A Day in the Life of the Internet is a large-scale data collection project undertaken by CADA and DNSOAC every year since 2006. 48 hours or 50 hours packet capture at root DNS servers. And source IP addresses of B and I data are anonymized, so I cannot use. This year, I analyzed ACEFHJKLM 9 of 13 root DNS server data. And the other data set is JP datasets. JP has 1.4 million registered domain names, and JP DNS servers serve approximately 1.6 billion queries per day. And I analyzed packet captures of all JP DNS servers around the same time as DNSOAC's DLT event. Then There are my interests of the evaluation, number of queries, average queries per second, number of query source addresses, status of recursion desired, query ratio of IP version 6, EDN 0, DNSSEC OK, ratio of IP version 6 query source address, ratio of IP addresses that send EDN 0, DNSSEC OK, root DNS key, and query ratio of each country. This graph shows collected queries at root DITL dataset, 48 hours, average queries per second. This graph shows increasing tendency, but slower than content size increase, about 5 times increase in these 8 years. Next graph shows number of queries from each IP addresses at root. Each IP address from at root 48 hours. The vertical, horizontal axis shows ranking of each IP address, and the vertical axis shows number of queries from each IP address. Number one address send 100 million or 800 million queries in 48 hours, very large number. And the graph shows the same tendency by years. Why they send over 1 million queries to root in 2 days? Some of them comes from type non-TLD queries and implementation bugs or DOS attacks. Then there are some types of strange data. In 2016 data at root, there are one type is senders of huge number of queries. Number one address sent 235 million queries in 2 days. 1,364 queries per second average. And the address sent recursion desires of with EDNS 0, DO bit set, and existing TLD various query name. I think they may be normal. However, the address didn't seem to use cache. A number to send about 100 million queries in 2 days, 600 query per second average. The address sent similar to number one. Number 3 sent 95 million queries in 2 days, 554 query per second average. And the address sent RD not set with EDNS 0, DO bit set. However, the address sent m2m.root-servers-net quad day and A6 only. Very strange. And the other type of strange addresses are IP addresses that send non-DNS packet or RD set only. My previous report at Nanog67 describes that many strange RD set queries observed in 2016 data. After detailed analysis, they were non-DNS packets generated by DOS attacks to root DNS servers. 58% of IP addresses sent non-DNS packets, and 4% of IP addresses sent RD1 query only in 2016 dataset. They may come from attacks, misconfigured hosts, and or bots. And these graphs shows non-DNS RD1 query only queries at root. Left graph shows number of query source IP addresses. Blue line shows normal recursion desired off, and orange line shows recursion desired set only, and gray line shows non-DNS packets. And ratio of IP addresses that send non-DNS packets is not so stable and very high in 2016 dataset, 58%. Number of non-DNS packets is similar to number of query source addresses. One address sent one query, one packet only. And the ratio of IP addresses that send RD set only is not stable, 4 to 20%, 4% in 2016 data. And right graph shows queries per second data. Ratio of RD1 queries is small and relatively stable, 4% in 2016. RD set query comes from stub resolvers, careless bots, careless measurements, unrelated to internet status. Ratio of IP addresses that send RD set only is 1 or 2% at JP dataset, smaller than root. And this graph shows hourly queries to root 2016 dataset. Root receives stable queries and 4 or 500,000 query per second average total, and 20 to 18,000 query per second RD set, 2 million RD unset client, full service resolvers, and 50,000 mix client, and 230,000 RD set only clients. However, April 6, 9 o'clock, there were many 10 million IP addresses that sent non-DNS packets only. This is 1 hour queries to each root, April 6, 9 o'clock. The black dot shows number of queries to each root. Number of queries to each root varied. And the purple part shows number of IP addresses that send non-DNS, those attack queries only. Irregular queries hit L and M only, derived from attacks. Then these graphs show irregular queries to L and M, April 6, 9 o'clock. This graph shows 5-minute queries to L and M. Number of 5-minute queries and number of IP addresses that send RD0, RD1 queries are relatively stable. Irregular attacks, destination port 53, non-DNS data started 9 o'clock to AM and changed to L at 9:10. Stopped at 9:40. Query source addresses may be forged or random. Packets contain 1020 octet 0 data, maybe those attacks. And this table shows comparison of RD0 and RD1 non-DNS at 2014-16 root. The table shows that queries from RD set only addresses rarely support IP version 6, Quad A, EDN0, DO, DNSSEC validation. Irregular non-DNS spikes and RD set queries do not show the status of the internet. Ignoring non-DNS and RD set queries is one effective idea to decrease effect of irregular DOS and stub resolver queries. This table shows query source ranking by countries at root 2016 RD0, recursion desired off. This table shows ratio of US and German IP addresses very high, 26% and 11%. US and China addresses generate 23% and 20% of root queries, very high. And number of queries divided by number of IP addresses are high in some countries. Next graph shows Asia Pacific version of query source ranking. Ratio of Asia Pacific countries' IP addresses is small, except some countries. Ratio of queries may depend on each country's population, but I didn't compare now. Number of queries divided by number of IP addresses are high in some countries: China, Korea, Taiwan, Indonesia, and Philippines. And next table shows query source ranking by countries at JP domain name this year. IP addresses in JP generated 38% of JP queries. JP domain name is well used in Japan. And IP addresses in United States generated 25% of JP queries. And United States uses largest number of IP addresses to resolve 26% of IP addresses that send queries to JP DNS servers. And next graph shows number of queries from each IP address per countries en route this year. Horizontal axis is ranking of each IP address, and vertical axis shows number of queries from each IP addresses. And strange query senders exist on all countries. Top query generators are Brazilian addresses, and the graph contains non-DNS packets and RD1 queries. Next graph shows number of queries from each IP addresses per countries in JP this year. IP addresses in Japan generate many, however, not significant queries to JP, because JPTLD is well used in Japan, and JP Zone has about 1.4 million delegations and one-day TTL. BZ resolvers may send 2.8 or more queries in 2 days. And top query senders are from United States and German or German addresses, and 10 million or more are too large numbers, I think. Next graph shows ratio of quad A queries. IP version 6 query type quad A is well used and almost stable, about 16%, green and yellow line. And IP version 4 query type A is about 64%. Ratio of IP addresses that send quad A queries is large, about 48% at root, 43% at JP. A half of IP addresses send quad A queries. The reason of the increase is that most of client applications and OSs send both A and quad A queries. Excluding addresses that send non-DNS or RD1 queries hide irregular decrease of ratio of IP addresses that send quad A queries at root, light blue line to deep blue line. Then ratio of quad A queries is still increasing. Next graph shows ratio of IP version 6 transport. IP version 6 transport is well used, about 7% at root, 12% at JP. Ratio of IP version 6 addresses has been increased 5% at root, at both root and JP. Excluding addresses that send non-DNS or RD1 queries hide irregular decrease of ratio of IP version 6 addresses at root, light blue line to deep blue line. IP version 6 usage may be still increasing or stable. Next graph shows ratio of EDNS0 DNSSEC OK queries. About 70 or 80% of all queries have EDNS0 and DO bit set. The query source know DNSSEC, at least the software support DNSSEC. Next graph shows ratio of EDNS0 DO IP addresses. DNSSEC protocol support in full service resolver is widely deployed. 70% of IP addresses at both root and JP support DNSSEC. And excluding addresses that send non-DNS packets and RD1 query only hides irregular decrease of IP address ratio, light blue gray line to orange and yellow line. And the next graph shows DNSSEC validation at root and JP. DNSSEC validators send root DNS key query every day. Red line shows ratio of IP addresses that send root DNS key queries. Currently 16% and still increasing. And DNSSEC validators send each JP domain name DS every 900 or 7200 seconds to JP. Dark line shows the ratio of IP addresses that send subdomain domain name.jp DS queries, and currently 9.7%. As a result, ratio of probable DNSSEC validators may be 9.7% or 16% now. These are findings. Queries to root DNS servers are increasing, but slower than content size, 5 times increase in these 8 years. And some addresses generate strange many queries. Some hosts send over 100 million queries in 2 days. And 100,000 addresses send over 1 million queries in 2 days. I think this number is very large. And IP version 6 query type quad is well used, almost stable, 16%. And IP version 4 type query type, 64%. IP version 6 transport is well used, 7% at root, 12% at JP. And ratio of IP version 6 addresses is increased, and 5% of query source IP addresses are IP version 6, both root and JP. And DNSSEC support is well deployed, 70 or 80% of addresses support. And the ratio of probable DNSSEC validators are still increasing, and now 9.7% or 16%. And DITL dataset may contain irregular data. April 6 to 9 o'clock UTC, 10 million IP addresses send those packets to M and L. And ignoring non-DNS packets and RD set is one effective idea to decrease effect of irregular those non-full service rollback queries. And that's all. Thank you.
Any question for Kazunori-san? I guess not. So this is for AP. Thank you. Thank you. For our other speakers. No, the show is not yet over. There is a last part of the movie. I have a small experience with Jeff. I saw the first presentation of Jeff at 2013, and after the ending of the presentation, I by myself I was telling, oh my God, these things happen in the internet, and these are the data he gave on 2013. On 2014, I have another chance to see another presentation of Jeff. I recite the same thing. Oh my God, these things happen in the internet, and these are the internets are going on. So when Jeff submitted these presentations, I was in the part of the PC. We definitely said, okay, fine, we have to see those presentations. What is Jeff is bringing to Sri Lanka, because he doesn't come to this part of the world very often. So next presentation, Jeff Houston.
Thanks a lot for that. Look, this is not one of those presentations, I'm sorry, but it just isn't. This is actually a bit of community consultation, because at times in the Secretariat, we're sort of forced to make decisions. And sometimes it's kind of easy and obvious. But other times those decisions are difficult and have implications. And this one in particular, if you followed the IETF's interdomain routing, secure interdomain routing working group, you would have seen one of those sort of, things that go pop, because it's been an extremely hot topic. And to be perfectly frank, in the Secretariat, we're not sure what we should do, because the choices available are difficult. So I'm going to go through this area and hopefully give you a picture of this. Has anyone got the slide changer? Oh, good. How much do you folk know about crypto? Who knows a heap about crypto? Okay. Who knows a little bit about crypto? Okay. When I say trust anchors, do you know what I'm talking about? Yes, no? Let's scare the crap out of you. This is scary, because everything we do on the internet relies on this, and most of it's bogus. And the fact that it works is faith, not engineering. That said, let's talk a little bit about this. You go to a web page, it's your bank. What it tries to do is to give you some reassurance that it really is your bank. And so what it does is it uses what we call a digital signature. Now, a digital signature is a very simple thing. You can take an arbitrary document and you hash it. God, computer science, second year, hashing algorithms, take a really big bunch of bits and create a smaller bunch of bits from it. Hopefully, different documents produce different hash sums. It's like taking a column of numbers and adding them up, right? It's a hash sum. And normally what you do then is you apply your secret key to that hash value and produce a unique string of bits. It's unique that only I could have done it with my key. Your key won't produce the same string of bits. So I present to you this digital signature that says it was really me, this is the document, you should trust it. Now, if we've met before, and I've given you my counterpart public key, we're okay. Because you can take that public key I gave you, check it against this signature that I signed with my private key, the two should interlock, and you can be assured of a few things. I said it, and no one else. And I really said it, and I can't deny that I said it, because I signed it. Irrefutable. This is good stuff, you'd think. But what if you and I have never met? And I can't send you my public key because I've never met you. What do you do with these bunch of bits? Well, the good folk at Netscape decided that they would create an interim solution back in '94, and they used a technique from the cryptographic area of the world that had been doing this for some time, where we have what's called public key certificates and hierarchies of trust. This is where it gets really scary. Open your browser, go to the extension setting, go to Advanced, click on List all the people who have issued certificates that you trust, and tell me how many you know. Anyone know more than 2? There are at least 1,000 on most of those lists. Some of them issue certificates for money. They don't care who you are. Some of them feature on Google's bad list, where they're issuing certificates that are absolutely fake, complete bullshit. And your browser trusts them. The screen will go green every single time. You have no idea who these people are, but there are at least 1,000 of them. This is your trust anchor set. And your machine implicitly, absolutely trusts not only those folk, but everyone they have certified. And everyone they have certified, it's a chain. So now, when you get a document with a key, it tries to find a link from someone you trust who's signed a certificate to someone else, who signed a certificate to someone else, who actually has produced that document that you're trying to validate. And when you press the impressive looking lock on your browser to say, why am I trusting this? It tells you why. That's meant to reassure you. The fact that it's complete nonsense is kind of a different problem. But that's how the entire system works. And any kind of public key infrastructure has a very similar property to this. There is one or more trust anchors that you implicitly trust completely for security, and they sign across other people who sign across other people, eventually getting to the thing you're actually trying to validate. And if you can make that chain of linkage work, you trust the end product. Whether you should or not, different problem. But that's the way this works. So what we're talking about here, that button, is the resource public key infrastructure. You might have heard about this. APNIC's been banging on about it for some years. There is no doubt that when we issue you with some addresses, we record your identity and the addresses we gave you in a database. And you look it up using whois, yeah? You could actually say that this is just a string of ASCII lies. How do you know it's really APNIC's database? How do you know the entry's correct? What does it mean when something's listed as Jeff Houston? It might not be me. How can you actually understand that what's being represented in that database is what APNIC did? How can you trust it? If you're appropriately skeptical, you shouldn't trust it. Because almost every part of that process can be subverted and you can be misled as to who has which address. And so to answer this over the last, God, really has been 16 years. Christ. I'm feeling old right now. Little ancient moment. Over the last 16 years, we've been trying to develop a system that underpins the registry with cryptography and secure cryptography. What we're actually trying to do is to allow the assertions in the database to also include your public key, so that you should be able to create a digital signature that says, those are my addresses, please route them, please sell them, whatever you want to do with them, they're mine. And the fact that I can make such a digital signature means that you can, if you will, validate the fact that I'm claiming control over them. So it's a PKI. It's a very conventional PKI. That means you need to have a trust anchor or more. As your browser shows, you can have thousands of them. But as you've also probably figured out from the browser world, having thousands of trust anchors is probably worse than having none. Because the more folk you trust, the more likely you're going to trust someone you really shouldn't have. So in some ways, we're trying to find a model for trust anchors which is constrained, useful, and robust. So what should that model look like? The one we came up with was actually a precise analogy of the number registries. The RIRs, the regional internet registries, did not create the number space. We are distribution agents for the IANA. So the numbers reside in the registries at IANA, and blocks were assigned to each of the regional internet registries, who then further assigned and allocated them onto ISPs, NIRs, whatever, right? And those registries run at the IANA record what they did and when. So in theory, you could set up this sort of RPKI going all the way up to the IANA. And what the IANA could do is generate a certificate for each RIR to say, well, here's the addresses that you control because we gave them to you. It matches what's in the registry. And we'll sign it with our private key, and we'll sign across your public key. And so the beauty about that is, as an end user, you just need one key, which is the IANA public key, and you can validate anything. Simple and effective. Or so you'd think. So there's a problem. And some of you are making it bigger as we speak. Because what you're doing is transferring addresses. You're buying and selling them because we ran out. And so some of you might have bought some addresses that were originally registered in ARIN or the RIPE NCC, and you're bringing them to APNIC. IANA didn't certify APNIC, IANA certified ARIN. So how do we get that chain of consistency for transferred addresses? This is where your brain explodes. Because if we want to keep the IANA model simple, we've got to invent complexity at the next level down. Bang. All of a sudden, every RIR needs to generate a certificate for the exported addresses for each of the possible other RIRs where those addresses have gone. This is awful stuff. It gets incredibly complex, and instead of each user having just one certificate for all the addresses they have, depending on how it came to them, they might have 2, 3, 4, or even 5. This is insane. You know, it is insane. But that's not everything. The other part of this is all of the RIRs need to play this game. Fails. Do this alone. And the RIPE NCC at this point is saying, we're not playing that game. So we're kind of stuck. We can't get there unless all of us are playing, and one of us is saying out loud, we're not playing this game. So what do we do now? In the interim, APNIC in the Secretariat made a decision. And the decision that we made was to take the little bit that's us. Need a laser pointer here somewhere. I'm gesticulating at the bit that's APNIC and all the certificates under it, and simulate what the other RIRs would have done for us. And so we have a trust anchor, which is a little bit like your browser. It's not just one. Inside that trust anchor are actually a collection of 5 trust points. Now, the reason why we did this is that it makes the transition to the bigger model a lot easier. We don't have to do very much at all. We'll just slide into it. We've done all the work. So we can go to a single IANA trust anchor at some point in the future with no major change. The self-signed certificates become IANA-issued certificates, and we're just kind of fine. But this is really complex. Every single time an address moves in and out of APNIC, we have to change the trust anchor. Every single time. So this stuff moves a lot of the time. There's a lot of dynamic behavior in it, and it's certainly complexity is your enemy. Because the more you're mucking around doing these root signing changes, the more likely it is you're going to have a whoops moment, drop something on the floor, and then that's catastrophic, particularly if someone's using it for routing. So we're nervous. As a Secretariat, we're kind of feeling we're very exposed on this, and certainly we're not exactly happy, but it seemed like the right thing. On the other hand, there are alternatives. The other 4 RIRs adopted a much simpler model. In the interim, they just produced a single trust anchor for themselves, self-signed certificate that said, these are all of our resources. Now, admittedly, when they change, they have to update this certificate, so there's still the same bookkeeping and updates, but it's a simpler structure. If and when we get an IANA trust anchor, that's a lot more work to do, because you've got to go and recreate that and then get all the way back to that. So this kind of model certainly is a long way from where you need to be, but you know, the other RIRs are doing it. You could go one step further if you really wanted to be kind of simple and have APNIC simply say, well, we'll just self-sign all the resources so that whenever anything changes, our trust anchor does not change. It's incredibly stable. We can leave the key in an offline mode. We never have to bring the key out. That's a really good thing in security practice. You know, life is happy. It is, of course, a complete lie. And that's not a good thing to do. APNIC does not own all the resources, and certifying the fact that we do is kind of stretching the truth well beyond its normal breaking point. But it's simple, it's stable, and operationally good. So what should we do? And at this point, the Secretariat's kind of sitting here going, we would value some comment, some thoughts, some ideas, some reactions from the community we serve, because we're not sure what we should do. Somewhere between staying where we are and being ready for an IANA trust anchor whenever that it comes, which relies on other RIRs getting to that point as well, which we're not sure when that's going to happen. Or we could move to a model that's consistent with what the other RIRs are doing today. Yeah. Takes us further away from a trust anchor, could be a problem politically. Or we can go to a really simple model, incredibly simple, but that sends its own messages which are unhelpful. Some thoughts about this have been written by the RIRs. Here's an internet draft that kind of expresses this latter model as a common model for the RIRs to go to. And certainly we in APNIC are interested in any reactions you might have to this. As I said, there's been a lot of feeling about this in the IETF, and in particular the issue of where does the root of trust come from in the number space? Should the RIRs have the ability to assert trust as themselves, or should they be linked into a model that definitively includes the IANA, despite the fact that some RIRs are taking their time to get there? So that's the presentation. It really is a case that we're searching for comments and feedback from you guys, because as a Secretariat, we feel a little bit lost on this one, and we're not sure where we should go, and we'd be happier if we had some support that we could point at from the community that would justify taking a particular decision. That's my talk. Any reactions? Thank you.
Question for Jeff?
Hi. Hi, Jeff. My name is Taiji from JPNIC. We have an RPK system, and we are trying to connect to the APNIC RPK system and do the same thing with APNIC. And as I mentioned in a different place, I am afraid of making complex CA structure. For example, if JPNIC does the same thing with APNIC, the CA structure will be multiplied or 5 times more, maybe. So, but actually, I don't have any clear comment for the solution, but actually, JPNIC RPK system is updates on the trust anchor certificate, because the trust anchor locator can locate only public key, but the certificate itself. Maybe we can solve or arrange the trust anchor certificate in APNIC, but it's very helpful for the any places we can discuss, or we can looking for the solution.
And the purpose of this presentation was to actually see if there were reactions where we could discuss this. So, you know, this is the time, this is the place, right? And as I said, I've tried to outline the essential compromise. Accuracy and alignment to the IANA registries creates incredible complexity in the certificate hierarchy, with multiple certificates spanning address issues, right? It's complex and it has failures. It's difficult. A much simpler structure almost ignores the IANA. Very simple structures that overclaim in all parts of the hierarchy, but they're simple and they're robust. And so there's this compromise on which way we want to slide the dial. Because we can slide it to quite extraordinary simplicity, but a lot of folk will think that we're ignoring the IANA and we're raising the flag of insurrection and we're declaring independence from a system that we shouldn't be declaring independence from. And that's a bad thing. But it's simple. If we go down a route of using an IANA trust anchor, we've got a lot of complexity on our hands, and that's a given. Now, we can do it, and it's doable, but all of you are going to get some of that complexity, as you point out in JPNIC. More certificates, more complex. But it's doable, and we'd like to understand which way you'd like us to go.
Thank you, Jeff.
Thank you.
So thank you, guys. So this is our end of our session.